Hello there. So let's turn to spectroscopy for the semester. Looking at infrared spectroscopy, we'll get on to proton NMR and carbon-13 nuclear magnetic resonance in the spring semester. So hydrocarbon molecules can absorb infrared radiation. If we look at the greater electromagnetic radiation spectrum, on the left we start with these longer wavelengths, and as we move to the right, moving to these shorter wavelengths, the wavelength is diminishing from the size of a building to the length of a human being, to butterflies, down to molecules, atoms, and then individual nuclei themselves. And so the speed of light from Einstein's equation is equal to the wavelength multiplied by nu, the frequency. The frequency, therefore, is equal to the speed of light divided by the wavelength. And so we can see mathematically that as that wavelength decreases, as we're seeing on our diagram from left to right, that decreasing wavelength causes an increase in the frequency. So the more intense radiation is on the right-hand side of our diagram with gamma rays, and the least intense radiation is on the left with radio waves. If we use our equation to work out the energy of a single photon of light, treating light like particulate matter, we see that Planck's constant multiplied by the frequency gives us the energy of a photon. Now we can incorporate our previous equation, which told us that the frequency was equal to the speed of light divided by the wavelength, and we can say that the energy of a photon is equal to Planck's constant multiplied by the speed of light divided by the wavelength. So we can see that the energy of a photon varies directly with the frequency, and the energy of a photon varies indirectly with the wavelength. As the frequency increases, the energy of a photon increases. But as the wavelength increases, the energy decreases. So we said that these molecules, these hydrocarbons, absorb infrared radiation. And the frequency of that radiation absorbed in the infrared range has to match the frequency of the vibration of the chemical bonds in the molecule. There's four main examples. Our first one here, what we call symmetrical stretching. If you can imagine these two bonds to the central atom behaving like your arms, and you're waving them or pumping them above your head in unison, so symmetrical stretching. Or if you thrust one arm up in the air and bring one arm down and then alternate arms up and down at the same time, that's what we call anti-symmetrical stretching. And then just waving your arms from side to side like you were doing jumping jacks. That's what we call in-plane bending, sometimes referred to as scissoring. You think of the action of a pair of scissors as they bend within the plane of the pair of scissors. And then finally, out of plane bending, what we sometimes call rocking, and that's like your legs kicking back and forth in front and behind your body. So that radiation absorbed has to match the frequency of the vibration of the chemical bonds. So if we look at our infrared spectroscopy machine, we've got our light source producing that infrared radiation, and the beam is split by a set of mirrors, splitting it into two halves. One half which will go through the sample as we switch through the range of infrared frequencies, and we'll see radiation being absorbed at particular frequencies by particular kinds of chemical bonds. Remember, the frequency of the radiation has to match the frequency of the bond's vibration. And different bonds between different atoms vibrate at different frequencies. Now the other half of the beam goes through the reference. That's just so we can subtract anything that's not being absorbed by the chemical sample itself. We rejoin the beams. They eventually hit the detector, and then we get a readout. Now that readout, you might think, would be the frequency compared to the energy being absorbed through the wavelength of the radiation. But we actually take the wave numbers for the graph, which is calculated by taking the wavelength over 1. So this gives us a number of waves per centimeter, rather than using the frequency, which is a number of waves per second. So if we look at our graph, we can see from left to right, the wave numbers are decreasing. And that goes alongside an increasing wavelength. Remember, as the wave numbers get smaller, the wavelength itself is actually getting greater. And so we've got the high energy radiation to the left because of a high frequency. And as we move to the right, the wavelength is increasing, and so the frequency is decreasing as we move to the right. Our baseline is actually across the top of the spectra, 100% transmission of the radiation. And as we move down, we're seeing greater and greater absorption of the infrared radiation. So right down at the bottom is 0% transmission, meaning that all the radiation of that frequency is being absorbed by the molecule. So let's look at a couple of examples. So two spectras here, and we have to decide whether it's a spectra for an alkyne or an alkene. And I've highlighted the chemical bonds which are of particular interest here. So in the first spectra, the first bond we see is at 3060, a sharp peak, a bit moderate intensity. And that's right in the range we expect for a carbon to hydrogen bond when the carbon is in a carbon to carbon double bond. So a carbon to hydrogen stretch for an alkene. We also see an absorption of infrared radiation for a carbon to hydrogen bond when the carbon is attached in a carbon to carbon triple bond, but the absorption is at much higher energy because the carbon here is just sp hybridized, while the carbon in the alkene is sp2 hybridized. The alkyne bond has greater s character, and the s atomic orbital is held closer to the nucleus, so that carbon to carbon triple bond is stiffer than a carbon to carbon double bond. And stiffer bonds absorb at much higher frequencies, much higher energies. So the CH bond, which is next door, is also stiffer, and we absorb energy up in the 3300 wave number range. Further evidence is from the absorptions at 1643 and 2120. The 1643 is about the middle of the range for a carbon to carbon double bond stretching. Range is mainly from 1680 to 1640. It can vary slightly if the bond becomes looser because of conjugation with other pi bonds nearby. So the carbon to carbon triple bond is much stiffer. stretching vibration again, and it's usually around about 2100 for the carbon-to-carbon triple bond. Our last piece of evidence is the carbon-to-hydrogen bond bending vibration, and we get a peak around about 900 for a carbon-to-hydrogen bond, which is attached to a double bond. So bending vibrations normally below 1400. We also see this carbon to hydrogen bending for a CH bond, which is attached to a carbon, which is part of the triple bond. But notice that it's normally much lower than the double bond CH bend, and it's also much broader than the double bond CH stretch, down about 600 rather than the 900 range, and a very broad and distinctive absorption peak. So all our evidence clearly points to the alkyne being our second molecule and the alkene being our first molecule. Let's take a look at another. This one, now trying to distinguish between an aldehyde and a ketone. So let's look at the peaks that we have again. First spectra, only really one significant peak. This one at 1720, which is right in the middle of our range for a carbon to oxygen double bond, a stretching vibration. The full range is about 1770 to 1670. Can sometimes be a bit lower if the bond becomes looser because of conjugation with other pi bonds and lone pairs again. Now that doesn't give us clarity because of course we're seeing a peak very close by in the second spectra at 1728, which is also for a carbon to oxygen stretching vibration. But the main distinction between an aldehyde and a ketone are these two peaks here, just above 2800 and just above 2700. These are CH stretches for a carbon which is double bonded to the oxygen in the aldehyde. A ketone does not have hydrogens attached to the carbonyl-carbon. So the aldehyde is our second spectra and the ketone is our first spectra. Again, let's take a look at some more. So the first peak we see is this big, broad thumbprint peak at 3324. That's right in the range we expect for an oxygen to hydrogen stretch when it's part of an alcohol. We also see the peak at 1069, which is in that area we expect, 1200 to 1000, for a carbon to oxygen single bond, next door to the oxygen to hydrogen peak, of course. The trouble is, of course, that a carboxylic acid has these same peaks. It has an OH stretch and a carbon to oxygen stretch as well. However, although the OH stretch is again broad for the carboxylic acid, we can see here that the position for that stretch is much lower, usually centered somewhere around 2900 to 2800, and it actually overlaps the CH stretching we see for an alkane. That overlap is not normally seen with an alcohol. So that OH stretch on a carboxylic acid is much lower in energy. The bond is less stiff. We also have the carbon to oxygen stretch, of course, down at 11:15. And the one thing we don't see with the alcohol is a stretch at 17:08, which is for the carbon to oxygen double bond itself. So once again, the carboxylic acid is the second one, and our alcohol is the first one.